I
Like,
yeah.
No.
You do.
You know everything doesn't like.
Just a joke.
It's a joke.
That's a spot.
Kind of like I did my.
Okay, you can turn to page 2. Page 2 in your packet.
Is that interesting?
So I think we skipped number 5 on page 2. So let me go over this with you, and then we'll do start worksheet 2. Okay, so on page 2, it's on that half sheet. It says the function g is shown in the graph. D of x equals x squared plus a divided by bx squared minus 3, which are the following to be the values of the constants a and b. So we're going to rely on the function and the graph to kind of help us gather some information. So for number 5, here's our function. Sorry. So we know that if the denominator, and also we see some asymptotes here, right? So we know that the denominator is where we look for asymptotes. So we can see some common links there. And how do we find asymptotes algebraically? So to find vertical asymptotes, we set the denominator equal to 0. Right. So let's go and do that. We know that if I set bx squared minus 3 equal to 0, I can look for the vertical asymptotes. Well, we already know where the vertical asymptotes are, right? Where are the vertical asymptotes? Yeah, 1 and -1. So x equals 1 and x equals -1. So I should be able to enter 1 in for x, because I already know what that value is. And I can use that to help me solve for b. So does it matter if I plug in 1 or -1? X is squared, right? So I'll get positive either way. So there's our strategy to solve for b. So our b value is 3. Okay, so now, what if, okay, so now I need to solve for a. What if I set the numerator equal to 0? What information could that give us? Do you guys remember? Denominator set equal to 0 helps us find vertical asymptotes. Numerator equal to 0 helps us find what?
Horizontal asymptotes.
Remember, horizontal asymptote is where we compare degrees, right? The horizontal asymptote is looking at the x squared is just going to be 1 over b, right? So that's something else.
Is it one of the intercepts?
Yeah, that's the x-intercept. If I set the numerator equal to 0, I get x-intercepts. If factors between numerator and denominator cancel out, then we get wholes, and ratio is the horizontal asymptotes. Now, if I set x squared plus a equal to 0, I get x-intercepts. But can I see x-intercepts already on the graph? What are they? Yeah, 2 and -2. So I know that my x-intercept is at 2 and -2, 0. So we already kind of know what the x-intercept is, and that will allow us to insert 2 in for x or -2 in for x, and we can solve for a that way. equals negative 4, b equals. Okay, did we do number 6? No, okay. So number 6 says identify vertical asymptotes. We know that's going to come from the denominator, but why don't we factor everything so we see what the leftover factors are in the denominator? Factor everything out, we should be able to see where that asymptote could be. You know, the x minus 1 is going to be related to holes. So what's our vertical asymptote? Yeah. Set that factor equal to 0. Solve for x. X is negative 2. Okay, any questions with page 2? All right, let's go ahead and start worksheet 2. And we have a mixture of different process or different problems here. Could be a limit, problems involving limits, involving real numbers, vertical asymptotes, one-sided limits, horizontal asymptotes. So we need to see if we can keep everything clear in the steps that we did. All right, so page 5. Okay, starting with number 1, limit as x approaches negative infinity. Sorry, yeah. All right, so which piecewise function can we choose?
X plus 5 over 2x minus 1.
Yeah, so less than 2, that also means x between negative infinity and 2. So that falls into this category as it continually extends to the left past our graph. So when we see infinity as our limit, what's our process?
It's negative 1.
Well, let's think about this. Hmm? We only do decimals if there's a what? If there's a
A number.
vertical asymptote,
Yeah.
right? Now, so we have a different process for infinity, right? Infinity or negative infinity, we always go and look at compare what?
Oh,
Compare degrees.
yes.
Yeah, compare degrees. So we don't want to jump into testing for values until we confirm what we're dealing with. Okay, so compare degrees. What do you notice about the degrees?
They're the same.
They're the same. So therefore, do we have a horizontal asymptote? Yes, and that just the ratio of the coefficients, right? Is equal to what? 1/2. Okay, so this 1/2 is the limit, but it's also technically the horizontal asymptote because this graph is going to flatten out at a y equals 1/2. Okay. So we compare degrees, right? If the degrees are the same, we take the ratio. If the denominator has a higher degree, we know the asymptote for the limit is 0. If the numerator has a higher degree, then we say there's no limit, but we're choosing between positive and negative infinity. And then we can maybe test -100 to choose between the options, right? We're only ever testing a value if we're having to choose between two options, right? Two remaining options. Okay, 2 from the left side of 2.
Same function.
Same function, right? We're approaching 2 from the left side of 2. So imagine a value has 1, 1.5, 1.6. Those are all values less than 2. Let's make sure we're very clear as to what the steps that we take. What's the first thing that we do? Plug in what? Plug in 2, right? Right. We don't want to do any decimals, not until we have confirmation to do that. Okay, so what happens when we insert 2? We get 7/0. So that tells us something very specific, right? What's happening there on the graph? Yep, there's a vertical asymptote. We know that the full limit, does it exist? The full limit doesn't exist, so we kind of have an idea that there is no limit, but this is asking for a one-sided limit. So we know that if we're headed towards an asymptote, there's only two options, right? It's either positive infinity or it's negative infinity. So now we can test, right? Now we have enough confirmation to understand, okay, now I'm choosing between my two options. This is the only time you're going to play with decimals. So what decimal can we test? Right, and I think this is what's potentially throwing a lot of students off, right? I think the tendency is we naturally want to start with this process, but if we start with this process too soon, and if it's not a vertical asymptote, then we're stuck with something that we're just going down the wrong path, right? So 1.9 and for x, right? 1.9 plus 5. So numerator, we have positive. Denominator, we know 2 times 2 is 4, so 2 times 1.9 is
Plus
less than 4, so 3 point something. 3 point something minus 4 is negative, therefore negative. All right, so we're really only doing this if we first confirm that there is a need to do that, right? We never touch with we never play with decimals unless there's a vertical asymptote. Okay, go ahead and try part C. Choosing a value to the right of 2, fall in that category of 2x minus 5. Remember, with limits, we never want to deal with points. So you're never going to look at this 12. You're never going to look at this 20. Right? Not going to play a role with any of the limit problems. Unless there's a problem that's asking for the order pair. Okay, part D is asking for the full limit. How do we approach that? Yep, compare the B and C, right? We know the full limit can't be evaluated using just one function because we see the graph is split on either side of 2. Again, this 12, this point plays no role in our limit. And we're comparing our directions from both sides, and one's headed towards -1, the other side is headed towards negative infinity. They're not in agreement, therefore limit
Does not
does
exist.
not exist. Use a function coming from the left side of 5. Coming from the right side of 5 for f. So from the right side of 5, this is not going to fall inside the interval. So we're looking for greater than 5 there. All right, first things first. What's that? Yeah, plug in 5, right? Got to see what's going on before we decide not to go too far into this. So what do we get?
Awesome.
Good. Negative 21 over 0. We know there's a vertical asymptote. We know the limit doesn't exist. But now we go back and realize it's not asking for the full limit. It's just asking for the behavior from one side. So you know there's only two options, right? It's either headed up or it's headed down. Because it's going to hit that wall. It's going to hit that asymptote wall. So now we can test what?
5.1.
Yeah. Yeah, the 5.1 is going to get squared before that negative is seen. So we get a numerator above, denominator 5 minus 5.1 is also negative, therefore positive. Limit as x approaches 5. We see this, the graph is split on either side of 5. We have to rely on one side of the limit. Do we have enough information to conclude? It doesn't exist, right? One side is 5, the other side is positive infinity. They're not in agreement. For h, find the appropriate piecewise function, which is 2x minus 5. Insert the 3 in, we get a real number. That's our limit, nothing more to do. Okay, for I, limit approaching positive infinity, which piecewise function? Good, the last one. Okay, so limit approaching infinity, we have a completely different mindset. We're not going to plug in real numbers, we're just going to do it. First step, compare degrees, right? What do you notice? Numerator is higher, which means that the limits doesn't exist because the graph is either increasing up towards positive infinity or is decreasing, right? There's not going to be an asymptote. There's not going to be a y value. So we're down to two options. How do we test between these two options? Plug in 100, right? Let's move in the direction that this graph is headed towards. Okay, numerator we get Denominator we get negative, so negative over negative is positive infinity. Okay, number 2. Step through continuity conditions, right? So let me highlight those steps. Let me leave this up here for a second. Any questions? Okay, so number 2, we have the step through continuity conditions, right? First, identify the C value, find it with a pair. Second condition, does the limit exist? If you can rely on one limit statement, you can do one limit statement, but if you are forced to have to rely on 2 limit statements, then you can do one side limit. See if they are in agreement. If the limit passes, then keep going to the third condition. But if the limit fails, then we stop and we say it's a non-removable discontinuity. So go through each continuity step. And I'll follow up with the steps after you guys had a chance to try it. What's our phi value?
3.
3, okay, so enter 3 into the function. Second condition, we need to find a limit. Can I rely on one limit statement?
Because they're different functions.
Yeah, different functions. I have split on either side of 3. I gotta see the approach, right? I gotta draw arrows. That's the visual representation, but algebraically, we have to do one side limit. So we'll do limit as x approaches 3 from the left side of 3, limit approaching 3 from the right side of 3. See if they agree. Okay, are these 2 in agreement?
No,
No, what can we conclude?
non-removable, discontinued.
Okay, before that, we're gonna say that the full limit doesn't exist. So you can say limit as x approaches 3 of f of x does not exist. And then we can stop. No need to move forward with another condition. We already know what type of discontinuity. Non-removable discontinuity at x equals 3. Make sure that you get to this point that you're actually making a full conclusion, right? That you're identifying that we're justifying why the limit doesn't exist with the step above, but we're finalizing, we're concluding that that's why the limit doesn't exist. All right, moving forward, next problem. Any questions? All right, try number 3. Okay, does anybody still need to look at 2? So number 3, it's asking for horizontal asymptotes. This is one of those strange functions, right? What's strange about these types of functions? Square root, okay? And visually, what's going to happen with horizontal asymptotes? How many are we going to have? 2, right? It's going to be something strange, right? There's going to be a split asymptote. The graph will look something like this. But once we find one asymptote, the other one is just the negative version of the same ratio. So we'll do limit as x approaches positive infinity first. Are the degrees matching?
Yes.
Yes, okay, it doesn't look like it initially, because the numerator is x to the first power, the denominator looks like it's x squared. But that x squared is under the square root, so we know those two will undo each other. The degrees are the same. So we just take the ratio of the coefficient, which is what? Square root of 6, right? We don't want to forget about that square root. That square root does have an impact on that 6. So that is one of the asymptotes. There's an asymptote at -2√6 if we move to the right. Where's the asymptote going to be if we move to the left? Positive, yeah. So the signs would just always be opposites of each other. So whatever you find for the ratio for one, you know the other one is going to cause a different sign to show up. Okay, number 4. Number 4 should feel like a quiz question, right? Confirming that you have first 0 over 0, and then conjugate method will take you down to the real number. Okay, check the answer key. That you should get 1/4. Okay, any questions with 4? Okay, so number 5, step through your continuity conditions. Will help you solve for decide which of the conditions it will fail, or whether it will be, or whether it does meet every condition. This is one of those strange ones where I like to, if it helps you, you can split this first expression into 2 inequalities, right? One that's less than 3 and one that's greater than 3. Welcome to write it this way if you like. And then just go through each of the conditions. Find the order pair, find a limit. And if the limit exists, then keep going. And then third condition, compare the first 2 conditions. And if they are not in agreement, we know that function is not continuous. But if they are, if everything is in agreement, if we can make every condition pass, then the function is continuous. First condition, order pair, f of 3 equals 6. Second condition, 1 limit statement or 2? Just 1, right? You can do 2, but you're just doing the same problem twice, so just do 1. confirm that you're gonna get 0 over 0. Once you do, you know there's a hole, the limit does exist. Factor the numerator. Reduce with one of the factors in the denominator. The limit does exist, it equals 6. What about we keep going, right? Third condition. Will the third condition pass?
Yes.
Yeah.
Yes, right? There's a hole in the graph. You see common factors that cancel out. There's a hole, but that hole is filled in nicely with this ordered pair. So all three conditions pass. If this point was elsewhere or this point didn't exist, then that hole would remain. But that first condition, it allows that hole to be filled in nicely. Our function is continuous at x equals 3. Okay, number 6, we have the function. Are the lines x equals 5 and -5 vertical asymptotes? Well, we know we can determine the vertical asymptotes from the denominator of your function, but we need everything factored out, right? So see if we can spend the time to factor out that function there. See if you can decide where that asymptote is. Yeah. Numerator factors, denominator factors. And then now we can identify where the hole is, right? The hole is at x equals 5 because we see common factors. Right? The denominator that does not go away, that's where you can find your vertical asymptote. Next part is asking, identify all horizontal asymptotes. So what does that mean? That means take the limit as x approaches what? Infinity, okay. So I go back to my original function. Doing x approaching infinity, I compare degrees, so the degree is the same. Yes, so ratio is 1, y equals 1. What if I do x approaching negative infinity? Will I get a different horizontal asymptote? Still the same, right? Still the same, right? The only time you're going to get 1 and -1 is if we do it with square roots, right? But we don't have any square roots. It's going to be one asymptote on either side. Doesn't matter if we're going right or going left. Either way, right? Positive or negative infinity, we're only one asymptote. Okay, let's see, part C. Part C says, is there a value that makes the function continuous at x equals 5? Well, we know there is a hole at 5, right? So whatever the limit is going to be where that hole is located. So we just go through our process, find the limit as x approaches 5, because we know that if it's only a hole, we should be able to find out where that hole is and fill that in. So plug in 5, we get 0 over 0. Factor, reduce, reevaluate. Okay. Wherever the limit is for a function that started off with 0 over 0 is also the location of the hole in the graph, right? And you can cancel out the factor, you know that there is the hole. If you find the limit, you're able to find the location of that hole. Okay, part D. We know that at -5, we already know that there's a vertical asymptote. So if there's a vertical asymptote, there's nothing that we can do to fill that gap, right? There's a vertical asymptote. It's a non-removable, right? This continuity. Okay, let's look at number 7. It's just a matter of visualizing where the graph is and see if we can see what we can conclude. Okay, so this is a instance of applying IBT. So IBT says if I want a guarantee of specific y value, I need there to be proof that the function is continuous, first of all. And second, is there points on either side above and below that target y value to ensure that the graph will cross over that target y value. So number 7 says, if a function is continuous, so we know that condition is taken care of, which of the following must be true? Can we guarantee a y value of -3 somewhere between 1 and 8? So we start off at -2 and we end up at 10. We never reach below -3. I mean, it's possible that the graph dips below -3 that we don't see, but based off of this table, we just can't guarantee it, right? Because we can imagine a situation where this graph is never going to cross -3. So, so IVT, yeah, does not apply. And we guarantee a y value of 0 between the x values of 1 and 8. So we're looking at these endpoints. Let's look at the y values. We have a y value of -2. And we have a y value of 6. Does 0 land between these two y values? It does, right? So if we're starting at -2, and if we rise up all the way to 6, there's no choice but the graph to cross through a y value of 0 somewhere on that interval. So we can say by IBT, since f of 1 equals -2, and -2 is lower than 0 and 0 is less than 6. 6 is coming from that endpoint. We know that there is at least one y value of 0 somewhere on that interval. Okay, third condition. Can I guarantee a y value of 9 between 1 and 8?
Yes.
Yes, maybe I'm not looking at 8, but I have 5, right? So I know that I can think of 5 as a quote unquote endpoint if I think of it as an endpoint within that interval. So I do see a value between lower than 9 and higher than 9. So we can make that conclusion because we have something to work from, right? And then I'm adjusting the interval because technically 1 to 5 is just a subset of 1 to 8. So. Right, with the last few minutes here, I want to see if we can sketch a graph from scratch. Now, there's something that we haven't seen quite yet. It's the fact that if we're approaching negative or positive infinity, and you see a number, that means that graph is going to exit with a horizontal asymptote in mind. So let me show you what that could look like. So here I meant to say sketch the graph of the function. So easy things first. I can find all the order pairs. There's only one. Right? Limit as x approaches -4. For the left side of -4 is -3. Limit as x approaches -2 equals 1. So if it's a full limit, then the graph has to approach that same y value from both sides of -2. Gotta have extension from both sides. And I'll do A last. I'll do the asymptotes last. Limit as x approaches 0 from the left side of 0 equals 2. I'm gonna connect these two. That fulfills that condition. Limit as x approaches 0 is undefined, so I'll just have that as an endpoint. I won't extend past that point for this branch. Limit as x approaches 3 from the right is -4. Limit as x approaches 4 is -infinity. I want the graph to go down in both directions. It's gonna be drawn towards that asymptote. Limit as x approaches 8 equals 3. Okay. Limit as x approaches infinity equals 8. So that means infinity means I'm gonna exit the graph. So as I exit the graph, what's gonna happen to that graph? Yeah, it's gonna flatten out. It's gonna flatten out at 8. So I find 8. I do a dotted line just to help indicate to me that my graph is flattening out at that towards that dotted line as I exit the graph. Okay, the left side, as I exit the graph to the left, is there an asymptote? -6. So somehow I have to make my graph exit and flatten out. Okay, we'll continuing practicing tomorrow. I'll have a health session tomorrow, fifth period. Tomorrow afternoon, 3:30, Wednesday morning, 7:15. I send you guys get a reminder that I sent on Sunday.
About signing up, yeah.
Yeah, so see if you can sign up, today or tomorrow, or for this week. Don't forget your phones. I'll remind you every day until all the students are signed up. Thanks.